Now let's look at more laws. The laws about the limits of transcendental functions. So we suppose let C be in the domain of each function. So the limit x approaches C of sine x, which is sine C. The limit x approaches C of cosine x, which is equal to cosine of C. The limit of x approaches C of tangent x, which is equal to tangent C. The limit x approaches C of secant x, which is equal to secant C. The limit x approaches C of cosecant x, which is equal to cosecant C. The limit x approaches C of cotangent x would be cotangent C. And the limit x approaches C of a to the x is equal to exponential function a to the c. And the limit x approaches C of natural log of x, which is equal to natural log of C. So here natural log means the logarithmic function with base e. E is a constant which is about 2.7. So here you can see for these kind of functions, right, transcendental functions, the limit is quite easy. It's just plug in the numbers. Okay, so now let's look at some examples. The first example, we want to know what is the limit x approaches 0 of sine x and the whole thing square. Right? Sometimes, so here are some conventions that sine x, the whole thing square, we can write as sine squared x. So that means you can take the limit. We know for the power function, right? A composite function. This is the outside function. Then this would be the limit x approaches 0 of sine x. Then take the square. So the limit of sine x approaches 0, which is sine 0, and then square. So which is sine 0 equals 0. So 0 squared, which is equal to 0. Okay, so now let's look at the limit x approaches e. E is a constant, about 2.7. Natural log x cubed. Right, take this limit. And this is we can use the law number 9, the basic law number 9, which is the law of composite function. This is the composite function, right, which is composed with natural log and x cubed. So we can take the limit for the inside, put it inside the natural log. Natural log is called outside function, right? So this is the limit x approaches e of e cubed. And this is the polynomial, so we know the polynomial for the limit is very easy. You just plug in the numbers, e cubed, right? Then we can use the properties of the natural log or logarithmic function. We can take the power 3 out, so it's the natural log of e. Natural log of e equals 1, so it's 3 times 1, so it's equal to 3. So here is some quick review for the natural log. So natural log of a to the b's power, which can be use the law of the logarithmic functions, which is b times natural log of a, right? natural log of 1, which is equal to 0. Natural log of e, which is the same as the log with base e of e, right? So this would be 1. And the logarithmic function, the graph for the logarithmic function, which is an increasing function, with the y-axis as its vertical asymptote. So it's an increasing function, right? So now let's look at some special limits. Special limits. Some problem we may need this result. So this is the first one, which is a very important one. This is the limit x approaches 0 of sine x over x, which is equal to 1. The second one, the limit x approaches 0 of 1 minus cosine x over x equals 0. The third one, which is actually the definition of the constant e. Right, where e from? E is this one, 1 plus x, then raised to the power 1 over x for the limit as x approaches 0, which is e. So the first one is really interesting. So now let's look at an interesting theorem, which is called the squeeze theorem. Squeeze theorem, which says if h of x is less than equal to f of x, less than equal to g of x, for almost all x in some interval containing a constant c. And if the limit x approaches c of h of x equals the limit x approaches c of g of x, which is equal to L, then the limit x approaches c of f of x, which is also equal to L. So this is called the squeeze theorem. So the both sides of this f, which is g and h, right? And both sides, when x approaches c, both sides will approach the same number L. Then the middle one must approach the same number L also. So let's look at the remark for the theorem. Let's look at the geometric meaning for this one. Okay, so this is the function f of x. Right, let's look at another function h of x, which is less than equal to. So this is c. This is c. Right, this is the h of x. So h of x is almost less than f of x, almost everywhere. Right, and this is the g function g. The g of x is also greater than equal to f of x almost everywhere around the c. So you can see when x approaches c from both sides of c, if this point is L, then for the h of x, it will approach L. It will approach L. approaches this point. For the g of x, it will also approach this point. So for the values on the f values, okay, on the f curve, there's no other choice. The points on the curve will have to approach this point, which have the value L. So this is the geometric meaning for this squeeze theorem.